Hello students, as you can see in today's video I will be talking about air resistance. So as you watch the video, please take notes in your notebooks and pause the video whenever you get lost at any point, and you can rewind and listen to the video over and over again. So by the end of this video, you should be able to understand that air resistance is a kind of frictional force. Remember, we have talked about frictional forces before, and you should be able to explain how air resistance changes with relative velocity. Okay, so before we move over to air resistance, let's do a review of Newton's laws of motion, which will help us to understand air resistance better. Newton's first law, what does it state? Please pause the video and restate Newton's first law. Okay, Newton's first law says that every object will remain in its state of rest or uniform velocity in a straight line unless it is acted upon by a net force. So if there is no net force, then the object will not accelerate. It cannot speed up, it cannot slow down, it cannot change direction. How about Newton's second law? Please pause the video and think about Newton's second law for a second. Okay, Newton's second law is simply expressed by the formula F equals ma, as you can remember. Force is proportional to acceleration, or acceleration is proportional to force. Newton's third law of motion, what does it say? Please pause the video for a second and think and write down Newton's third law of motion. Okay, Newton's third law of motion says that action and reaction are always equal and opposite. Action force and reaction forces are equal and opposite in direction. Also, we have talked about balanced and unbalanced forces, but this is a better recap of balanced and unbalanced forces. Let's consider a camel that is standing on the road. Please pause the video and think, what forces are acting on this camel? Okay, the forces acting on this camel are the weight of the camel, which is the pull of gravity by the earth, and there is a normal contact force upward, which is the push of the rod on the camel. These two forces are balanced. In other words, the net force on the camel is 0 for the weight, and the normal reaction force are equal in magnitude, but opposite in direction. So they are balanced. That's why the camel does not accelerate. Now let's say that we take away the road. Then if we take away the road, the normal contact force will disappear, because the normal contact force is provided by the road. So what will happen to the camel? The camel will accelerate downwards, because there is a net force on the camel, so it accelerates downward. Consider also a number of objects. This animal, pause the video and think to yourself, is this animal moving or not moving? Okay, this animal, the forces on the animal are balanced, so the animal either is not moving or it is moving at a constant velocity. If it is moving, then it's moving at a constant velocity. If it is not moving, or it is not moving. Those are the only two conditions. Second, for this other animal, the forward force is bigger than the backward force. So this animal is accelerating forward. This third animal, the backward force is bigger than the forward force, but the animal is moving forward, so the animal must be decelerating. There might be a third animal, fourth animal that is lying there. There are no forces acting on the animal, so the animal is not moving at all. Correct? Yeah. Okay. Consider, for example, a car. If this car has an engine force forward and it is moving forward, then there will be a backward force, which is the push of the air on the car. The car is moving forward, so there is a backward force, the push of the air on the car. If you sit in this car, you put your hand outside, you can feel the push of this air in the reverse direction. Now, as this car accelerates forward, the push, the backward push will increase, but the engine force cannot increase. So there will come a time when the backward force, which is the push of the air on the car, will be the same as the engine force. When at this point, in this third case, the forces on the car are balanced. So the car will have to move at a constant velocity according to Newton's first law of motion, correct? If we take away the engine force, we stop accelerating the car or we stop applying the engine force on the car, then the car will certainly decelerate and come to rest, because the only force acting on it will be the air resistance, which is the backward force. Remember that air resistance is a force that acts against anything that moves through air. If the thing moves through water, there will be another resistance. You can call it fluid resistance, water resistance. So this car is moving forward. It has air resistance on it. The air resistance gets larger when the object moves faster in air. This car is moving slowly. The air resistance on it is small. This other car is faster. The air resistance on it is very large. We can reduce air resistance by streamlining the object or giving it an aerodynamic shape. Aerodynamic shape is, for example, this truck here. As you can see on the front of the truck, there's this gap. So when the truck is moving forward, the air will push on the truck. So the air resistance is very large. If we want to reduce the air resistance on the truck, the push of the air on the truck, we can put this little thing here on top of this so that the air will be able to slide over it. So the air will slide over it and the air resistance becomes smaller. Streamlining also works for objects such as a boat that is moving in water. You can see the front of the boat is streamlined so that the water can slide through the boat. A fish, for example, is naturally streamlined. By nature, it is streamlined because the water can slide over the fish. Terminal velocity. Consider a skydiver. Let's say you have a skydiver. He falls out of the airplane. What forces are acting on the skydiver? Pause the video and think about it. Okay, you got it right. There is the weight of the skydiver. So the skydiver is going to accelerate downwards. As the skydiver accelerates downwards, there is going to be the push of the air or the air resistance on the skydiver. But the skydiver keeps accelerating, so the air resistance becomes bigger and bigger. At some point in time, the air resistance will be equal to the weight of the skydiver, because weight cannot change, of course. So the weight and the air resistance will be the same. At this point, the skydiver will be moving at a constant velocity. We call that velocity terminal velocity. It's the same as the terminal velocity at which the car, you remember the car we saw before, was moving. So, because this skydiver is moving at a very high velocity and he doesn't want to hit the floor or the ground with that speed, so what will he do? He will open his parachute. When he opens the parachute, then the air resistance becomes very large. As air resistance becomes very large, he will decelerate. He slows down, correct? As he slows down, the air resistance will become smaller again until it becomes equal to weight again. When it is equal to weight, he will continue to move at another terminal velocity. But this terminal velocity is smaller than the previous terminal velocity. Why? Because he has already slowed down in this case, correct? So that is how terminal velocity works. If the skydiver, so if we want to plot a graph of velocity against time for the skydiver, we will have this shape. First shape is when he falls out of the airplane, his speed increases, and then he reaches terminal velocity because because air resistance will be increasing, so he will reach a constant velocity at some point. And then when he opens his parachute, he slows down very quickly and reaches a second terminal velocity. He moves at that second terminal velocity until he hits the ground. If he was on the moon there is, it's in space, so there is no air, of course, so there will be no air resistance. So what will happen? Think a little bit. What will happen? What will be the difference on the moon? Pause the video and think for a while. Okay, you got it correct. On the moon, there is no air resistance, so he will continue to accelerate until he hits the ground. But that acceleration is smaller than in the Earth, so the slope of the moon's graph is smaller than the slope of the Earth's graph initially, correct? Because the pull of the moon is much smaller. Okay, here are a few questions for you to answer. After watching this video, you should be able to answer these questions correctly. First question is, an object moving at constant velocity has a net force acting on it, true or false? Constant velocity has a net force acting on it, true or false? The correct answer is false. There's no net force acting on it because the velocity is constant. Second, air resistance increases with speed, true or false? Of course, true. Air resistance increases with speed. Question number 3, an object falling at terminal velocity has no net force on it, true or false? You answered correct. It is true. There is no net force on the object. Fourth question, if an object falls on the moon, its terminal velocity is greater than on the Earth, true or false? Think a little bit. Oh, that is false. There is no terminal velocity on the moon, so that's a trick question. The fifth question, terminal velocity is the same for all objects, light and heavy, true or false? Oh, of course, that's false, because the weight of the objects will be different, right? So the speed at which it reaches terminal velocity will be different, since the air resistance will reach at different times. Okay, thank you very much, and see you in class tomorrow. Prepare to